Hello, Paul Beckwith, University of Ottawa, Laboratory for Paleoclimatology. For the sake of brevity, I'm going to get right into the report. So for a proper intro, talking about, to see what I'm really talking about, I'm talking about the warming Arctic, the linkages to extreme weather events at mid-latitudes in the Northern Hemisphere. Okay, so there's a list of proposed physical processes that may play important roles in linking Arctic change to mid-latitude climate. So the list is from high to low confidence. So increasing geopotential thickness over the polar cap. Okay, hot air rises. If it's cold air, it's heavier, it's dense, it sticks closer to the surface. So as you go up from the surface of the Earth up in altitude, then the pressure drops. If the air is cold, the pressure will drop quicker because the weight of the air that you go above is increasing more quickly. So we call that the geopotential thickness or the geopotential height. Okay, so a given pressure, for example, 500 millibar, you might have to go up 5.5 kilometers. Okay, if the air is cold, you go up 5.2 kilometers. If the air is warm, you have to go up 5.7 kilometers. Okay, there's a difference. Okay, so the increasing geopotential thickness over the polar cap, the Arctic is warming. And because it's warming, the air, you have to have more air to reach a certain pressure. So you have to go up higher. The air is thinner. It's hot. It expands. Okay, so increasing geopotential thickness over the polar cap, the polar cap is warming. Weakening of the thermal winds, okay, weakening of the thermal wind, the heat wind. Well, the thermal winds, basically, if there's a large thermal difference, large temperature difference, the Arctic's really cold, the equator's warm, that large temperature difference sets up faster winds. Jet streams are faster. Okay, as the temperature rises in the Arctic a lot faster than the rest of the planet, especially the global average and the equator, then those temperature differences decrease, so the thermal winds weaken. Modulating the stratosphere to troposphere coupling. Okay, we don't talk much about the stratosphere. The ozone is up there. We talk mostly about the troposphere, where we live, weather occurs in the troposphere, lower atmosphere. On average, the border between these is called the tropopause. It's about 11 kilometers high, but it's actually about 17 kilometers high at the equator because the air is warm, takes up more space, expands, and it's about 7.5 kilometers over the Arctic. So the air is cold and gets compressed. And of course, it's interesting because the ice on Greenland, right, the ice can be 3 kilometers thick. You can be 3 kilometers up, because the ice is 3 kilometers thick and then it's on bedrock. So if you're standing on the top of the highest point on Greenland, the ice cap, you're about halfway up through the atmosphere, which is interesting. Okay, so there's couplings that are changing. You've heard of the polar vortex being shattered, screwing up weather over North America. Well, there's a stratospheric vortex and a tropospheric vortex, and the sea ice decline actually can have an impact on breaking up the stratospheric vortex. I'm going to talk about all of these details. Exciting anomalous planetary waves or stationary Rossby wave trains in winter and modulating transient synoptic waves in summer. Okay, it's not exciting in terms of excitement. It's excitement in terms of, it's a physics term, basically. If you excite an atom, you get the atom to move more quickly. Okay, you're putting more energy into it. So you can get these anomalous, unusual planetary waves going around the planet, or stationary Rossby wave trains that get stuck in place, causing extreme weather in winter, causing extreme cold, for example, over eastern North America in winter. Well, where's climate change? Where's global warming? Modulating transient synoptic waves in summer. Synoptic waves, synoptics is sort of continental size, like North America. So you get these waves set up, and these waves are modified by what's happening in the Arctic. Okay, altering storm tracks and behavior of blockings. Okay, storms are moving in different places. Storms basically track jet streams. So if jet streams move in different places and are wavier, the troughs and crests of the waves are in different places, and they'll interact with mountain ranges and topography, or temperature differences between land, ocean, or temperature difference between ocean and ice. And the behavior of these storm tracks is altered. More of them are going further north up into the Arctic as the jet stream becomes wavier. They're actually crossing the equator, as I've shown, the jet streams connecting from the northern hemisphere to the southern hemisphere. Okay, these are all points I'm making. They're not in here, but so I'm elaborating and giving you a lot more information that's in this document. And they'll be in a document when 100 scientists meet in 5 or 10 years. They'll be in those documents. So it's good. We'll get there. Increasing the frequency of occurrence of summer wave resonances. Okay, the pathway considered most robust is the propagation of planetary Rossby waves excited by the diminished Barents-Kara Sea ice. So in the Barents Sea and the Kara Sea, the ice is kaput, basically. It's vanishing so much. And what that can do is that changes that's like becomes like a fixed point in the jet streams, if you like. So then they behave a certain way and they intensify. The Siberian high gets higher and we get these cold Eurasian winters. Okay, so that's a very robust thing. Of course, this is a summary, so those are all things. So what the workshop, an important goal was to hasten progress towards consensus understanding and find out where the knowledge gaps are. What do we know? What are we sure we know, or at least have scientific consensus on? And what do we know nothing about? What do we need to study? What are the key missing things that we're missing? Okay, so one of the things is that due to the remoteness and harsh environmental conditions of the Arctic, in situ, observational time series are highly limited spatially and temporally. Okay, you have a field trip, you go out, you're only in one region and you're not there very long. So temporally too short, spatially you're only looking at one part of the Arctic. That's why we use satellites to monitor it, but you have to ground truth the satellites, so you need the field trips to do that. So some recommendations on observational data sets are, we need a lot more Arctic observations, right? It's funny, you read a scientific paper and it says, we recommend that more research be done. And that's the most idiotic thing that anybody can say, right? Like, have you ever seen a scientific paper that says, well, we've thoroughly investigated this, we've learned everything that's possible to know about this subject, and therefore we don't recommend that any other scientist in the future moving out needs to even revisit or research this topic because we've closed the case on it. No research is needed. I mean, obviously, we need research all the time and more research. And to end a paper saying more research is needed, I have a pet peeve about that. So anyway, we need more observations in the Arctic. We need sea ice, ocean surface forcing data sets. I'm surprised those don't exist. Create physically based sea ice, ocean surface forcing data sets. Surely they exist. I mean, our world's changing. The Arctic is crucial. We need to, obviously, this is a huge gap. Systematically employ proven and new metrics. And, if we have some metrics, way of measuring something at mid-latitudes or at the equatorial in the tropics, then can we employ it systematically in the Arctic? Also the Antarctic, for that matter. This is good. Analyze paleoclimate data and new, longer observational data sets. This is crucial because the models The models are failing miserably in terms of sea ice, for example. So we need to look at the paleoclimate data. What happened in the past when we were warmer? What did the ice look like? Things like that. And we can't rely so much on the models. And when you do this, you get a very crazy picture about methane, for example, and permafrost. Utilize new observational and analysis methods that extend beyond correlative relationships. And consider both established and new theories of atmospheric and ocean dynamics to interpret and guide observational and studies. Okay, and then modeling experiments. Okay, we acknowledge that models provide the primary tools of gaining a mechanical, how do things work? How do the gears fit together? What moves what? What leads, what lags? Mechanistic understanding of variability and change in the Arctic and at mid-latitudes. Coordinating modeling studies should include a hierarchy of models from conceptual single component or coupled models to complex atmospheric global climate models, fully coupled or system models. Okay, so what we're doing is these would be these simplest models. Basically, you know, we can have regional models that are very high resolution, but they won't cover the Earth, of course. We can have different temporal, so it depends on the spatial grid size, if you like, of the model, and also the temporal time step of the model. We need all different, at all scales. And use the data to force models with consistent boundary forcing. So use the data to set up the boundary and run the model. So there should be a modeling task force, okay? There's something called CMIP. We need PAMIP, Polar Amplification Model Intercomparison Project, okay? So this would be a new umbrella group to set up, have a modeling task force to coordinate the data, coordinate runs, etc. Have everything open access, all the data, and promote analysis within the community of coordinated modeling experiments. Have the modelers focus more on what's going on in the Arctic. Why is Arctic amplification occurring, and how is it linking to mid-latitudes? Okay, so those things are, okay, so basically those are the things that the paper is recommending. Okay, so the first chapter is focusing on Arctic amplification. Okay, so the idea is to, what are all the different processes that cause the Arctic to warm rapidly, and how does each process individually affect the Arctic, how the Arctic warming that occurs influence the mid-latitude weather and climate variability. Now, this is interesting. The Arctic has warmed more than twice as fast as the global average since the mid-20th century. This is Arctic amplification, but it's been further enhanced. So, I said 80, I had this, the beginning. 1990, I had the dates, I said it slightly differently in my intro. 1998 to 2012, the warming rate, this is very important. I haven't seen this mentioned before in the literature. The warming rate is more than 6 times the global average. This is a 2017 paper. Okay, so that the Arctic's warming at twice the rate doesn't hold. You know, 1998 to 2012, 6 times. And I've been saying for years it's 5 to 8 times. Depends on how you define the Arctic. You know, are you above the 60-degree north? Are you above the Arctic Circle, 66 and 2/3? Are you above the tree line? Are you above, you know, whatever? Are you above the -5-degree isotherm, average annual temperature isotherm? Anyway, this is interesting. The high sensitivity of the Arctic climate change has been known for some time. And then they say, you know, 1975. So here's a paper 43 years ago. There was a paper that said the Arctic is going to warm quicker. So it says, beginning with this early paper and reiterated recently. Well, excuse me, what'd you do in the last 43 years? Reiterated recently. Okay, the high sensitive, this is kind of important. The high sensitivity of the Arctic climate to external forcing has been largely attributed to reduction of Arctic surface albedo. Okay, but we've evolved our understanding in the last couple of decades. There's other mechanisms that may be more important, thus altering the currently accepted chain of causality. And the other mechanisms are things like heat transport up into the Arctic, etc., because the jet streams are wavy. But the root cause is that the Arctic is getting darker. That's the root cause. So, you know, I think this should be reworded. Okay, now this is crazy here. For brevity, we limit the discussion of recent Arctic changes to surface temperature and sea ice. That's it. There's other notable changes. Greenland, let's not worry about sea level rise from Greenland tossing all its ice. Permafrost degradation. Let's not talk about the permafrost degrading, methane going up, warming the Arctic. Crazy to ignore.